In this video, I will be giving a demonstration of what we call a geometric series and showing you some handy calculator methods on the TI calculators. So this example is really motivated by something known as Zeno's paradox. And Zeno was an ancient Greek philosopher, lived in the BC 400s. Actually, he had a number of different paradoxes that he is famous for, but this one is used often in mathematics discussions. So, to demonstrate this particular one of Zeno's paradoxes, you can imagine that we have somebody who lives in a city, um, the city by the bay, and wants to get away and travel to the country. So I'm imagining that our character is heading to a pastoral town, um, with churches and fields, cows, barns, so forth. I don't want to get too carried away here. Get back to the math. Um, in any case, so the traveler is going to go from the city to the country, take a little break, take a walk. And that total journey distance is 3 miles. Well, at some point along the way, at some time or point in the journey, the traveler would have gone 1/3 of the distance that they had to travel. And in this case, that would be 1 mile. And there would be 2 miles remaining. Well, the traveler keeps traveling along, and at some point along the journey, he would have gone, or the traveler would have gone another third of that remaining distance. And this time the traveler would have gone, there were 2 miles remaining, so that would have been 1/3 of 2 miles, so 2/3 of a mile. And instead of 2 miles remaining, there would be 1 1/3 mile remaining, and I'll write that as 4/3. So I'm just kind of updating the amount of distance left. So again, at some point along the way, there's another third of the remaining distance, that 4/3 remaining. And so that distance would be, instead of 2/3, it would be 1/3 times 4/3, which is 4/9. So that remaining distance would be 4/9. So if we start to think about it as chunks of, or different steps in the journey, we could maybe think of this as the n=0 step. The traveler had gone 1 mile at that point, and then say the n=1 step, the traveler had gone 1 mile plus the next 2/3 of a mile. And then the next step, in this case, the traveler would have gone 1 plus 2/3 plus 4/9 miles. And we could continue this process, chop off another, travel another 1/3 of the remaining distance, chop off another 1/3 of the remaining distance, chop off another 1/3 of the remaining distance, chop off another. And see, Zeno would argue, well, when does this process end? There is no point in time where I can't continue to chop off another third and chop off another third. And he would argue that you could never reach the destination with this reasoning. So that's why it was known as Zeno's paradox. In modern mathematics, we refer to this as something called a series. And this particular type of series is a geometric series. And there are many different types of series. And this class is not about studying all those different types of series. This class is really about looking at a phenomenon and pondering it, thinking about ancient, Zeno as an ancient Greek philosopher, and pondering the question, would the traveler ever actually get there? Well, we know the traveler does get there. We know both that the traveler does travel the 3 miles and arrive at the destination, and we know in so doing the traveler passes through each one of these different 1/3 chunks of the journey. And we can think about this journey in terms of this idea of, well, these are going to be called partial sums. They're partial distance, they're partial parts of the journey. And one of the things that mathematicians do is they look for patterns. I'm seeing a pattern. Do you see the same pattern? And then I would say at the n equal fourth step here, to get that next distance traveled, the question in my mind is what 1/3 of the remaining distance did the traveler pass through? Well, I'm seeing a pattern in the numerator: 2, 4, 8. The next one would be 16. That's 2 times 8. And in the denominator, I'm seeing 3, 9, 27. Well, the next one would be 81. And I could go back and do all the math and show you those fractions work out, but I'm not gonna do that. I'm just focused on the pattern right now, because that other part would take 20 minutes, and I'm trying to keep the video short. If you really want to see that, though, send me a message and I'll do another video and show you how you can confirm that these numbers that are coming from the pattern are the correct numbers. Well, a lot of times it's useful to bring up some mathematical notation just because it makes things simpler, or it makes things seem complicated, I know, but it allows us to write really long patterns and ideas in a more shorthand notation. So just summarizing what we saw in the last example, and using some mathematical notation, the S that I'm writing stands for sum. The subscript means it's one of the partial sums in a long, long chain of an infinitely long chain of partial sums. This process can really go on forever if you think about it, right? I mean, I have to use my imagination to see that. This should be a 4. And then again, seeing the pattern. And I could keep doing that, just following the pattern. I can also think in general. And this is when you really start getting into some powerful ways of thinking mathematically. I'm going to put an ellipsis in here, which means this pattern continues. And then I have to think about, well, what would this term of this sum look like? This was the 0 term. This was the first term. That's 2/3 to the first power. That's 2/3 to the second power. That's 2/3 to the third power. 2/3 to the fourth power. This would be 2/3 to the nth power. Now, depending on how large n is, there could be a lot of arithmetic here. As a matter of fact, just figuring out s sub 4 could be very, very complicated. Well, we're lucky because we have this really powerful calculator that can help us with the computations. And for example, if I wanted to calculate this s sub 4 partial term, I mean, I could type it in, just say 1 plus 2/3 plus 4/9. And I want the answer back as a fraction. So let me show you how to get the answer back as a fraction. If you press the math key, the first thing that pops up as an option is arrow to frac. That means give me the answer as a fraction rather than a decimal. And so I see that the answer is 211/81. And I'm wondering how many, I want to think about that. Now that is a number of miles. So at that point in the journey, the traveler would have gone 211 divided by 81 miles. It's a little bit hard to read that number. And so I want to think about it as a mixed number. Again, I'm going kind of deep into the arithmetic now, but I want to think about it as a mixed number. And so what I'm going to do is I'm going to go and I press math, go to num, and then I'm going to choose f part. And what f part is the fractional part. So mixed numbers consists of a whole number part and a fractional part. And so right now what I want to do is convert this, or find the fractional part of this. So there's a whole number part. That's going to be 2 because the total journey is 3 miles. So I know the traveler's gone more than 2 miles. What fraction of a mile after 2 miles, though, of the remaining 1 mile? That's what this is going to tell us. And again, I want that number back as a fraction, so I'm going to put that frac part here again. So 49. So what this means is the travelers traveled 2 49/81 miles. And so I can let me go back to the table. So this is a table similar to the one in your homework. So it's fine with me if you just use the calculator for these computations. And I'm going to show you do a couple of these here to demonstrate what I'm talking about. Now, some of these you could just probably fill in and just see the pattern. Like this is 1, and then 2/3, 4/9, 8/27. The next one would be 16/81. And then 2 times 16 is 32. And then 3 times 81 is 243. And this would be 2 times 32 is 64. 3 times 243. Wait a minute now. 9. 3 times 4 is 12. 729. So again, as we go along, though, these computations are going to be more and more complex. And so again, it's fine with me if you use the calculator. Oh shoot, I think I wrote those in the wrong place too. Or something happened there. Let me fix that. Holy smokes. I just saw this in the wrong spot there. That's 32, 243, and this one would be 64, 7/29. Okay, and just again to confirm these two, this if my formula is correct, then when I take 2/3 and raise it, this circumflex means exponent. The older calculators won't make a little box up here and put the number as an exponent. It'll leave that circumflex or that caret. It works just the same. And the exponent here for this one would be 5, so I'm just going to check that. And again, I want the answer as a fraction, so I'm going to say fracket. So there's my 32 243s. And second enter is a really handy feature. I just press second enter, and what that does is it brings back the previous command. It's a bit of a shortcut. So there's this next cell would be 2/3 to the n, 2/3 to the 6th power, which is the 64, 7/29. So that was right. And then again, second enter. So you can see filling in this table, once you know how to use the calculator, can be done pretty efficiently. So those fractions start to get kind of crazy. I'm not going to fill them all in because I think you get the idea. Oh, okay. So I'm glad I did that one. So notice here it's no longer writing the number as a fraction. What ends up happening is these numbers get the decimal approximations of even some of these rational numbers get pretty long even before they repeat sometimes and stuff like that. And so since the calculator really has a memory limitation in terms of how many of those decimal places it can remember, at some point when we start to deal with these types of really small additions, fractions that have, really long decimals representations, they'll start to truncate or they'll start to round off and have error. So this one tells me that when I got to 2/3 to the 10 power, the decimal approximation was just too far away that the calculator couldn't remember and come back to the fractional form. So that sounds kind of long-winded, I know, but that's what's happening. And you'll see that happen on some of these examples. And all computers run into this problem. It's not just the calculator. And so for this particular example, it would be okay with me. It would be, I mean, could do all of this by hand and figure out these fractions, but I don't expect you to do that. So when you get down here and you're only getting decimals back instead of fractions, go ahead and write the decimal approximation there. That's fine. Now, looking at these partial sums, I actually see a mistake in my table right here, but that'll be apparent I'll do that one as an example just to illustrate. But these are the partial sums. Now let me go back to a plain screen here for a minute and just write down the calculator command to do these partial sums. So in this example, we had S sub n, and it was equal to 1 plus 2/3 plus 4/9 dot. I'm just going to put the ellipsis here. And then in the pattern, we're seeing that this is 2/3 to the n power, right? Oops, to the nth power. And it turns out, sort of as a handy thing, that each of these sums is 2/3 raised to a pattern, or to a power, I should say. 2/3 to the 0 is 1. 2/3 to the first power is 2/3. 2/3 to the second power is 4/9. The pattern, those powers continue, and we get down here to the last one, which is 2/3 to the n power. And each one of these, whatever we put in here for n, we can always do this arithmetic. The arithmetic can get really difficult by hand, but we can always do that arithmetic. Well, it turns out we can do these partial sums on the calculator, but it's a little bit complicated. And I want to write out on what the calculator coding. I consider this really, we're starting to really program the calculator right now. And really what I'm doing is I'm giving the calculator embedded set of commands to do. So that exponent's going to be in, comma, and then we have to specify the variable, comma, and then the starting point for in is 0, because that's how we set up our series. And then we get down to this last term. Oh, how far do we want to go? Well, that depends. The one I wanted to check is going to, I think it was 4, so maybe I put 4. And so and that wouldn't be in, actually. I have to change this. So I'm kind of sliding between notations here. I have to be careful. It's complicated. So S4 on the calculator, S sub 4 would equal sum, parenthesis, sequence, parenthesis, 2/3 to the in, comma, 0, comma, 4, close parentheses. So I'm just going to clear this out. And so I need to we're going to do sum. Where's that located? That's second stat. And then arrow to math. Choice 5 is sum. And then I need sequence. So we go second stat, OPS, down to 5. And then we need to have 2/3. So I put a parenthesis, 2 divided by 3, close the parenthesis. This is the exponent key, the circumflex key. On my calculator, it pops it up as an exponent. Your calculator may just put the symbol on the screen. Same thing either way. And this is alpha. In is going to be our what's called the variable. And we'll go comma, alpha, in again. And we're going to go from 0 to 4, close parentheses, close parentheses. And I want the number back as a fraction. So I'm going to go math frac, press enter. There it is. And we had that earlier, 211 over 81. We can do really, the nice thing about the calculator is we can do a lot of different partial sums. So we could do like the S sub 12 partial sum, for example. That would be sum, sequence, 2/3, in 0, 12. The nice thing about the calculator too is once I program this in to do other partial sums, I just press second enter, brings back the previous command, change the 4. It's a little bit tricky because right now when the calculator cursor is flashing a solid rectangle, it's in overwrite mode. So when I press the 1, it'll overwrite it. But now I want to insert, so I can press second, delete, and I'm really selecting INS for insert. And that's where I can put the 2. And then, yeah, so you can go in and bring back the previous command, edit it, and then press enter. And so you can see now the calculator is overflowing the decimal approximation. So it can't give the fractional form anymore at n equal 12. But that's fine. What it tells me is that the traveler's gone 2.98458 miles. So it's getting pretty close to the destination. He's getting close to the destination, the pastoral nice rural town, but he's not quite there yet. Um, I'm going to go ahead and press second enter because I'm curious at, that's, and I'm going to get rid of the frac part now. There's no point in doing that because we're beyond the ability for the calculator to give me fractions anymore. These are all going to be approximations from here on out. So suppose I'm interested in looking at, well, okay, we look at 100 or 101 of these partial sums. That means the traveler's gone through 100, 1/3 of the distances. What does this come back to? The calculator's got to, oh, it's finally popping back and saying 3. Okay, well, is it actually 3? Maybe. Well, actually, it's not. It's close to 3, the sum. It's not quite 3. We've just blown back completely by the calculator's ability to store numbers now. And so it just gives back the exact number 3. But in fact, it's not quite 3. It's just getting closer to 3. Let me do one more. Let me back this up a little bit. And instead of being trying to go straight for 100 like that, let me do this. So see, now we're at 2.99939 miles. And say we're at now 30 steps. Make that 30. Let's see. Now we're at 2.99999. And then we go 40. And really, we're talking about 41 divisions. So you can kind of see what's happening. And what'll end up happening now, all of these are rational numbers that we're talking about. So they're all exact numbers. They're not quite 3. But the calculator is just not able to keep those numbers with enough accuracy. At some point, it's going to overflow. See, we're getting close. At some point, it's just going to round the number to 3 and call it a 3. So what's going on mathematically here? Now, again, I don't want to spend a ton of time on this, but I do want to talk briefly about the idea of convergence. It's really a mathematical idea. So what we're talking about is S sub n, and I don't expect you to remember this notation. I'm not going to quiz you on it or anything like that, but I just want to show it to you so you've seen it. That's how I would write this sum that I've been talking about up here mathematically. And the important thing to remember, and really what we're interested in here is what happens to this sum as n gets larger and larger. Well, the 2/3 number that's getting added on, the 2/3 to the nth power number that's getting added on, is just getting smaller and smaller and smaller and smaller. It doesn't ever quite go to 0, but it gets so close to 0 that it becomes impossible for the calculator to even really store anymore. It's just gone. And so the calculator comes back with 3. The way we think about this mathematically is in terms of something that Newton came up with, and I think Leibniz and Newton both, but the idea of a limit. And what we would say is the 3 miles is the limit. That's as far as the traveler is going to go. They can't go any further than that. The sum can't get any bigger than 3. And so what we say is that the sum is equal to the limit, LIM is the notation we go, as n goes to infinity, so there's that infinity symbol cropping up, of the sum, and actually I don't need those parentheses, but I drew them. They're not wrong to be there, but they're not necessary, so... Okay, but it's the limit of the sum, and then we can say that is equal to 3. So the idea here is the limit idea, and the idea that even though this infinite process can go on forever, it can't go past 3. And so we'll say the limit of this sum, infinitely long, and that's the thing to see. This sum really goes on to infinity. As n gets larger, there are more terms in the sum goes on forever, but it has a finite number that we call its limit. And there's another word we use here that I might just mention. We say the sum converges. Okay, So again, just some ideas to get out there. So this is a similar table to the one in your homework, and I just wanted to illustrate that you can use the calculator to fill in this table to do this homework problem. It's fine with me. Um, and actually, there's an error in my table anyway, so let me fix that. And I'm going to use the calculator to fix it, as a matter of fact. So um, to find S sub n here for this example, okay. Oh, and the other thing I want to do, and I want to do an example for students who I know there are some of you, or maybe out there, I'm sure there are some of you out there saying, my calculator doesn't look like Professor Olson's, and it's true, because you have something called Stat Wizards turned on, and if you got your calculator new and it has Stat Wizards as a, I guess you would call it an app, it's on, the default setting for it's on, so I turned mine off, hoping to make my calculator look more like the other calculators out there. But let's see if I can find this. Okay. Okay, so you see StatWeb. And actually, I should also mention, I'm in the catalog menu. That was second function 0 for catalog. And this shows all of the functions on the calculator, every command. So if you're forgetting where something is, you can, and they're alphabetical, so you can just scroll through and find what you're looking for. And some of the things aren't even in a menu on the calculator, they only exist in the catalog. So I'm going to choose Stat Wizards off. Oh, wait, I did the wrong thing. I want to turn them on. Doggone it. Yeah, I can't talk and think at the same time. Now I'm going up from the bottom because I think it might be closer to the bottom than the top, what I'm looking for. So you can scroll either way in these menus. You can scroll up from the bottom or down from the top. There we go. I want to turn them on. Okay, now let me go through the partial sum here for the table that we're talking about for this example. So I need to go second stat to math and choose sum. And I need to go second stat into OPS and choose sequence. And in fact, in math, sometimes we say that we have the sum of the sequence. All right, so that's what was supposed to be in there. I'm gonna clear it out and show you how to put it in here by hand. So the first thing we have to enter, and notice this is where the wizard kicks in. So it's handy because it's a menu-driven kind of feature on the calculator. So it prompts you for what each piece needs to be. The expression in this case is this part I've written right here. This is 2/3, and we want it in parentheses, raised to the alpha in power, and the variable is n, so you maybe have a blank there, but you would just press alpha in, and we're going to go from start is 0, and we're going this one to the second n equal 2 part of the table, and then paste puts it into brings it up onto the home screen in the proper format. And let's see, this one's small, or this one is early enough in the sequence or in the series that I can get a fraction form. So let's look at it as a fraction. So that's 19/9. So this was a mistake over here in the table. This is really 19/9, which is so this was wrong. This is 19/9. That's 2 1/9. All right. And let's see. So to get this value right here, I'm going to use the recall feature. I'm going to go second enter. That brings back the previous command, and I can just edit the 2 and make it a 3. 65/27. I want to, you could write the answer as 65/27 here if you wanted to. It's okay with me. Because again, the class isn't really about, I mean, part of the nice thing about writing these as whole numbers is we're talking about miles, and it's nice to think about the whole mile part that's been traveled and then the fractional mile part. But then we're really kind of heading off with the problem into a more kind of, I guess, abstract place. But I will show you one feature the calculator has. If I want to write this as a mixed number, one of the things I need to figure out is what's the fractional part of the number. And so there is a feature on the calculator called F part. So I just pressed math, I arrowed over to number, and now I'm choosing F part. And I want the F part of 65/27. And this time I want it as a fraction, so that's 17/24. So this whole number should be 2 and 17/24. Now, at some point in the table, you're really not going to be able to do these problems. Not going to be able to do these problems on the calculator as fractions, and I don't expect you to do all the arithmetic either to convert these to fractions. So let me just do a couple of different ones. Let me do this part of the cell, right? Or let's do this n equal 8 part for this column. So to do that, I would take 2/3 and raise it to the 8th power. So you could just write that number 0.0390184, say, and write that as your answer. That's fine. And then for the partial sums part of it, just use the calculator to do each of these partial sums. So like, for example, for that same n equal 8 example, I would just make the 3 and 8 here. And I need another parenthesis on that. I might have deleted it on accident. And then press enter. And so again, 2.92196 or something. You could just write that in there as a decimal approximation. That's no problem. Okay. Well, that's it for this video. Please send me any messages if you have any questions. I'm happy to answer any of your questions on the message board. Okay, see you next time.